and then our team got really organized. So we will go to share screen. Okay, we are here. So today we will be discussing what I term as the most powerful word in the ANS fourth system. Powerful in that it does so much work under one word. It has more dimensions. It takes about 5 variables to support it. So in one word, you are interacting with quite a number of variables, which we will see as we proceed. The purpose of it, or the use of it, is that it'll take an IEEE 64-bit floating point number and process it and breaks it apart into its components, makes them very easy for application use. And primarily, it's used internally in Win32 for its floating point format, which is that's not on me. Okay, so Win32 uses it for its floating point formats, and there are about 3. It'll do scientific, it'll do exponential, it'll do decimal with a decimal point. But you then say, well, what if I want to put in commas and dollar signs, and what if I want to put in special characters? And if I'm in Europe and I want to use comma for a decimal point, what do I do? So you write your own. So the IEEE 64-bit floating point format consists of a signed bit and then an exponent, which is 11 bits, and the significand, which is 52 bits, which is the actual numerical value you're processing. And in the older world, it's been called a mantissa, which was kind of a holdover from logarithm days. The range is quite amazing on this. You can go 2 times 10 to the minus 38. Could you imagine a number with 38 with 10 followed by or 1 followed by 38 by 308 zeros? Of course, you don't have a total precision in that range. The precision is about 16 decimal digits. So even though the U.S. dollar is deflating remarkably or inflating remarkably, 16 decimal digits will still cover the U.S. dollar amount. I'm not quite sure about yen. So here's the definition of represent. As you see, it has a number of input parameters. First, it has a floating point number, F1, on the floating point stack. On the data stack, it has an address in which you want the conversion to take place, and N, which is the number of digits you want the conversion to result in. And then the word will return from that floating point the value of the exponent, the value of the sign, a flag on completion, and an ASCII decimal string placed and the address as a counted string at the address that you specify. And if this all takes place, you end up with a true flag. If you have a false flag resulting, then the exponent is set to the hex number you see there, 7 with a bunch of Fs. And then the contents of the address are no longer the converted number. Instead, it's an ASCII string giving you the source of error. And these are returned from the floating point processor in your computer with representations for not a number, infinity, and a couple of other types of error conditions. In all the work I've done, I've never seen an error condition like this. So apparently all the numbers that I get in and out and formatted with are translatable. So the actions that the word represent does is, the first thing it does is it extracts the sign. It then extracts the exponent, placing it into a decimal value, and it extracts the significand, which is placed from a number between 0 and to less than 1. I believe this is all done in the floating point processor. Then it rounds to the number of digits specified by the value precision, which you specify and select, and then it presents the string in a list of n significant digits. And finally, that string is an ASCII counted string. So the outputs are all very manageable, and they are all nicely parsed out for you. And then, of course, you have a simple error routine to catch the exceptions. So to be able to use represent, the first is you need two text buffers. The first is $F temp, and in Win32 in the hidden vocabulary, there's a couple of internally used text buffers that are allowable. And then for output, I use PAD. PAD has 160 bytes before its storage area and 160 bytes after. So from PAD, the 160 bytes to the left is used for integer input-output. The 160 bytes to the right of it are used for text preparation for floating point output. So your requirement then is you specify the precision that you want the output digit, then you call represent, and then you will get these three values resulting, and then you format your output from left to right. Now, an integer process going forth is done at least significant digit first, and it proceeds as of Chinese and Japanese right to left, and Hebrew right to left. The floating point is processed as a string, which is formatted from left to right, most significant digit first. And this is because you're concatenating a bunch of strings. At the result, you get the address of the string and a byte count, just as you would as output from numerical output. So here's our goal for the day. I want to take a floating point number, such as we see here, minus 123, a bunch of zeros with 59 decimal as an exponential number. And I want to go into a financial format. So I want a leading dollar sign. If it's a negative number, a minus sign, and then the integer value separated by commas with a decimal point, and then the number of cents at the end. So that is our goal for the day. There's a number of support words that are built into Win32, which of course it is using. The first one is place, which places a string it places a string from C address 1 in length. So it starts with a counted string, and then it appends that, or it places that directly at the C address 2. So we just transplanted a string. We copied a counted string from one location to another. The second one, though, is to concatenate or add a string. So once you've started your string with place, then use plus place to add to it. So this is used to add, in our case, selectively add ASCII digits to the input. We first transport the leading portion into our output buffer, and then selectively we take additional digits into it. And then along the way, you want to add characters, typically a decimal point, a dollar sign, a minus sign, other individual characters. So C plus place, you give it the address of your output string, and it will append that one character to it. So these do the bulk of the work. So here are the support words that leading up to my usage. The first is that we have a value called offset, and this gives us the byte offset to the string that we're working from. Singles copies across n number, a specific number of characters. So character by character, we can transport from the input string to the output string. And that is done by this $F temp is the source. The offset plus is the offset to the character we're processing, and then pad plus place puts it into the output string. And then the +2 offset increments the offset. So offset scans across from left to right on our input string. And the mathematics of place takes care of the output string. To transport 3 characters in between the commas, we have a triple. So in that case, we do a plus place, but in this case, it is instead of giving us the number of characters to transport, the 3 pad transport 3 characters to pad, and after the plus place, we see 3 +2 dollar offset, and that increments the offset. So this will chunk across 3 characters at a time. The nice thing is here, originally I did this with do loops, and so I spent a lot of time writing do loops, handling single characters, and then I realized I could parse it into singles and triples, and that really cleaned up the code. Finally, we want to place individual characters, and so place decimal places appends a decimal point to the string, and place comma adds a comma. So these are the workhorse program elements that translate characters and then add special characters to it. So my demo in this case is demo B. The input is a floating point stack number F1, and then decimals is the number of decimal points I wish to be to the right of the decimal point. And then what will result at the end is the address and count, which is suitable for typing. Because I am processing as many as 5 parameters in the same word, originally I started doing this using stack manipulation, and it really got messy. So I haven't really used locals a lot, but I found out this was the ideal application for locals, because you can give your key elements a name, and from now on, you are not doing stack manipulation. You just, when you want the exponent, you just call exponent and you've got it. So the locals in this case accept decimals from the input, and then exponent and sign are declared but not initialized. This is the setup. Pad off sets pad as a 0 length string, and then 0 to offset initializes our input scanner. fdup duplicates our floating point number, and now we call represent. So represent takes the input decimal, it locates the temporary storage area and selects the number of decimal points we want, does that conversion we talked about. And at the end, we get that error flag. So 0 equals abort error says it will catch and report if there's a formatting error. If all proceeds well, then at that point we have the sign and the exponent on the stack. So those go in and initialize the locals. Now we've done all of this. The purpose is to find the exponent, because when we are translating the number, we really don't know how many digits are present. And we know we want 2 decimals at the end, but we don't know how many digits are on the left. And so we don't know how many characters to allow for. So by obtaining we know the decimals number, we've now obtained the exponent. We add the 2 together, and then we put that into the Win32/4 precision value, set precision. So at that point, set precision now works in conjunction with represent to figure out how many characters to process. Now we do the translation again. So we go into our temporary variable temp. We select the number of digits to scan, and also this is our does rounding. The precision sets the rounding. We call represent. We've already tested the number. We know it's error-free, so we just drop the flag. And now we reload sign and exponent. So this is our final process ready for translation. Since we're going into a numerical format, we do the ASCII plus pad C place. That puts our $sign out in front. And then we call the sign local. If it is true, non-zero, it means we have a negative value. So in that case, we apply the ASCII minus sign, and then C++ puts it into the input string. So now we've taken care of the dollar sign and the optional minus, and now the remaining of the word does the heavy lifting. The critical value in this case is exponent, because exponent is the number of digits to the left of the decimal point. So buying a 3/mod, we now separate that out and we get the number of single digits that are present in the number and the number of triples. So the triples tell us how many groups of 3 are required, and then the leading singles is to the very left. We'll either have 0, 1, or 2 singles. Now we go into a case statement. So in the case of 0 triples, then that's very simple. In this case, we just call the word for singles, and that singles then takes the number of leading digits, either 0, 1, or 2, and using that word up above, transfers that many number of singles across. And the N is in parentheses because it's on the stack. Remember, we've done the triples and singles conversion. The triples has been accepted, and that leaves the singles number on the stack. That's passed to the word singles. And then at this point, we then place a decimal point. So this is the case for a number less than 100. Next case, if we have a number 100 and above, 100 and above is 3 decimals. So it could be 100, 1,000, or 10,000 in that range. In this case, then we look at how many singles there are, and we can 0, 1, or 2. So the words there very nicely parse out into handling the 3 different cases. If you have no singles, 1 single, or 2 single. In the case, for example, of 2 singles, we process the 2 single digits come across. We then place a comma, and then we place a triple, and then finally place a decimal point. So it reads just like you would on the text. Process the singles, process the comma, take care of the triple that follows, and then put in the decimal point. Next larger case, this handles 100,000s, millions, and 10 millions. So it's very similar to above, except they're a little bit bigger. The 0 case is triples only, so it handles 2 triples. The case of 1 says there's 1 single, so it's put out in front, then a comma, then 2 triples. And finally, if there's 2 leading digits, this is in the 10 million range and above. We do 2 singles, the comma, the triple, comma, and so on. And finally, we clean up the case structures. And this is the Euchre case that's a part of almost Forth these days. And I must admit, it was remarkably clean and error-free. When I wrote this, if I remember right, it ran the first time. Once I corrected little spelling mistakes, the structure came out perfectly the first time, which was in some ways amazing. And finally, at the end, we process the number of decimals. We have specified we want 2 decimals in this, and that means we just take the number 2 and pass it to singles, and so it goes chunk. After the decimal point, we do our pad. And now looking back on it, I realized I could parse out the placing a decimal, because at the end of every one of these sequences there's a place decimal, but the place decimal could have been just as well done one time only down at the bottom. So there's always room for improvement. At the bottom, then we do pad, which gets us the address of the conversion buffer, and count gives us our count. Now we're ready to output. So here's our examples we're testing. So I put in the number to begin with, minus 1.5789. I specified 2 decimal points, 2 decimal places, and the precision takes care of the rounding. So notice the 1.5 1.57. When it rounds, there's an 8 to the right. So the 1.57 becomes 1.58. So the rounding is taking care of us magically. And as the numbers grow, you see they go all the way down to 1,230,000 with 58 cents. And that is the result. Do we have any questions or comments?
I find it fascinating that you dug into this word, Bill, because it's definitely the processing of both the parsing and the output of numbers. I think is one of the sort of unavoidable pieces of complexity in a fourth implementation. So it's interesting that it sounds like in Win32 implementation, they leaned into a bunch of words that are not themselves part of the standard, so they had to do quite a bit to actually build up that facility, which I think is interesting.
Yeah, the floating point formatting in and out is really elaborate, shall we say. I mean, you like words that are 1 or 2 lines long. Well, a couple of these words are like 20, 25 words long, indented very carefully, heavily structured if-thens, many little, many little tweaks necessary to put the stuff in the right place. I was really not able to take one of their prototype words and rebuild it into my word. I had to start from scratch. This is 3 generations. I did it the first time with a quick hack, and it sort of kind of worked. And then I did a second one, and then it got pretty complicated with do loops and trying to handle all the punctuation. And finally, the third pass came along with that factoring, and it fell into place. And it also, there was a significant amount of learning because I had to learn the conventions and technique, but it worked out amazingly well. Any other comments? Otherwise, we will now turn it back to Kevin. Thank you very much for your rapt attention.
Thank you, Bill. I wanted to mention that Bowman has a Gameduino 2 book. I just saw on Amazon. I'm going to track it down and give you a link in the chat. So it is time for the screenshot. So turn on your camera, everybody. I keep saying if you're on the lam, turn off your camera or log off. But you're going to be on the YouTube anyway, so you were logged in. I wonder if there's a way to just not appear in the roster, but still watch the Zoom. I guess you wait until it's on YouTube and watch it there. Are we ready, Brad? Brad is muted, but he looks intent.
The second one turned out a little better, so
let's go with it. I wanted to ask how many of you are not RSVP'd on MeetUp for this meeting. It's important to us that we accurately represent our attendance, and I'm pleased to see that there are 18 of you here, counting me, I guess. And it would be great if you would, prior to the meeting or even after the fact or in the middle of the meeting, maybe now, go to MeetUp and say, yes, I'm here at this SVFig-ish Zoom meeting.
Kevin,
yeah.
I really am confused where MeetUp does anything. Every time I go in there, they keep wanting to know a bunch of personal information about me, and I don't want 20 more emails.
Right.
I got 1,800 as it is now.
I think you can switch them off, but if you don't want to switch them off and you don't want to have anything to do with Meetup other than to read the agenda, you can go straight to the agenda, and there it is. Send me a well, uh, if it's hard, don't do it. You know, I don't want to annoy anybody, but I do want to pad our attendance. That's why I say, you know, if you're going to watch the YouTube, if you're sure you're going to watch at least some of the YouTube, count yourself as being here.